Now we talk about open closed instruments. This is where, you have a pipe, an instrument, and it's closed on one end and then it's open on the other. And this is the other kind of category. Clarinets are an example of open closed instruments. So what we have to consider here with open closed instruments is, how do the harmonics work here? So we're going to unpack that here with a open closed instrument picture. So let's go ahead and draw that. So let's draw our pipe, and it's closed on this end, and then it's open on the other. And so let's go ahead and draw what this could look like, the air inside. So one of the things we have to know here is that there's going to be a node on the closed end always. And that's because the air can't spread out or compress, right at that end. So we have a node, and then the first harmonic, we would go to an antinode like this. So we have let's draw the air inside, and then we'll get to a compression at the end. So this is a node and then a compression. So what this looks like is, if we draw the wave on top of it, it goes for a node to compression. And then what we want to do is draw the rest of the wave. So then we would go back to a node and then a rarefaction, then a node, and then a compression. And so what we actually have here, though, is once we get back to the node here, right? So we have the node here, then we have compression, then we have a node, then we have a rarefaction, and then a node, right? And so if L represents the length of the tube here, we actually have to do 4 times L to be able to get the wavelength. So V equals frequency, or N, yeah, let's unpack. So V equals frequency times wavelength, right? So in this case, 4L is the wavelength here. So V equals frequency times 4L, and therefore divide both sides by 4L. So V frequency equals V over 4L in this case, and that's for the first harmonic. Now, it turns out again where we have the multiple here, N. So in this case, we have the first harmonic there, and then what we're going to do is unpack what happens with the next harmonic. So again, the node at this end, antinode at that end. Split second later, this is going to be a rarefaction, right? So it's going to flip from a compression to rarefaction back and forth very quickly. And so, 4L for that. Okay, so let's go ahead and draw the next harmonic. So let's draw the tube here, closed at this end. And in this case, with the next harmonic, if we start out here with the node, we know that this has to be an antinode. I don't think I said that yet. You have to have a node at this end, you have to have an antinode at the open end. So it's a node at the closed end, antinode at the open end. So we know that, with the first one we had the node and then a compression, or a node and rarefaction. And this one we're going to have to add another antinode. And so let's do that. We'll start with a node, and then we'll go to compression. Then we have a node, and then we have the rarefaction. So we have the node, compression, node, antinode, which would in this case rarefaction. So what this would look like is you get from node to compression, node, rarefaction. And then to draw the rest of the wavelength, it would be like this. Now, what's interesting here is if this is still L, right? L is the length of the pipe. Then if we, want to compare that to the wavelength, we would have to go a little bit further, right? So this is, if we break it up into the portions, here's a portion, right? Into the node, here's another portion, here's another portion, and then here's another portion. And so what ends up happening here, we actually have the same equation. Frequency equals NV over 4L. But in this case, how much is L compared to the full wavelength? Well, it's 3/4 of it, right? So you have a third here, a third here, a third here, out of the four parts. And so what ends up happening is it skips the second harmonic and you go straight to the third. So in other words, you have V equals frequency over 3, 4L. And because L here, is only 3/4 of the full wavelength, then, when we flip this to be 4/3, right? 4/3 L is equal to the wavelength. And we place that in here, V equals frequency times wavelength. And so we have V equals frequency times 4/3 L, right? And then we divide both sides by 4/3 L. So you have V over 4/3 L is equal to the frequency. And so if these are both on the denominator, we're going to multiply the top and bottom by 3/4. 3/4. So this is gone, this is gone, this is gone, this is gone, and then we have this, right? And so this is the actual equation here where n is the integer, and it actually only has odd harmonics. It skips the even harmonics. And that's a huge thing here, right? So in a clarinet, for instance, if you play clarinet, it's only going to play the odd harmonics. And that's really significant because it's going to have its own combination of those odd harmonics, because we know instruments have more than one harmonic. Just like with stringed instruments, you have more than one harmonic at the same time. In wind instruments, you have the same thing. You have more than one harmonic, and so it's the superposition of those, and you get your own unique combination of those in there. So if we were to draw this vertically, we would see the node at this end, and we'd have a compression node, rarefaction, and then in this case here, we have L. 3/4 of wavelength is L, or 4/3 of L equals wavelength. And we just saw there with that, we get our N harmonic there with 3, so it skips the second harmonic. And so the equation that we have, the frequency of open and closed, will be NV over 4L, where N is the harmonic number, and we only in this case get the odd harmonics. So when we look at different instruments, wind escapes on a flute, and with brass instruments, the length itself actually changes. So the factor of L, right, with an instrument is huge, right? With brass, you change the length of it. With the wind, or with the flute, for instance, you just change where the air is going out, and that effectively changes L for the instrument. And so the longer the instrument, the deeper it is. So if we take a look at a organ pipe, this would be, a large organ pipe, about 15 meters, which would be, very, very large. Let's go ahead and calculate the first 3 harmonics and see if you can draw the first 3 harmonics. Now remember, with open closed, you have only odd harmonics, so this will be 1, 3, and 5. And so go ahead and try this. Go ahead and try to draw all 3. When you draw the 5th harmonic, which is the third in this set, you're just going to add another node and an antinode, and then you can calculate each of these as well. So what we're going to assume here is the speed of sound is 343 meters per second. So go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play to continue. Okay, so we have the node, we have the antinode, this is the first harmonic. The third harmonic, node, antinode, node, antinode. And then for the 5th harmonic, we'll draw that in a second. First harmonic, I just had you draw the first 2 in the series. We'll draw the 3rd together. Or the 5th, which is the 3rd in the series. Should get 17.5 hertz for the 3rd harmonic, and then the 5th harmonic, this would actually be the only one that you could hear, right? Because you couldn't hear this one, and you can't hear this one. It's below the audible range, and so you would have that. So with the 5th harmonic, what would happen? You would have a node. In this case here, we had node, antinode, node, antinode. Then we just have an additional one. So we would have node, antinode, node, antinode, node, antinode. We would just add another one. So, this could be a compression, and a node, and then a rarefaction, and a node, and then a compression, something like that.